So the topic for my thesis was on incorporating the stochasticity of quantum machine learning into classical models. Just a very general overview of the presentation you're about to see. I'm going to first introduce the motivations for this work and what we're trying to accomplish before getting into the background that forms the case study. And this is going to consist of just some basic quantum computing fundamentals for the novice before we introduce, in short, the long short-term memory model that studied within. Then a brief introduction to the test cases that were run will be provided before we delve into the work and analysis performed. Then I'll be wrapping things up by introducing some discussion points before giving my closing remarks on the topic. So, as an introduction, quantum computing was largely brought about in the 80s and 90s from early proponents such as Feynman, Bernstein, Vazirani, and more. And through work of these people, we've come to find that there's a classification of problems not solvable in polynomial time on classical computing that we can, in fact, solve in polynomial time when applying quantum mechanics. Now, the most famous of these is Shor's prime integer factorization algorithm, introduced in 1993, which is a large force for why quantum computing is still being studied. Now, this gives, compared to some of the best classical algorithms, a exponential decrease in the number of operations for success. Another famous one, just to mention, is Grover's search algorithm, where we see a drop from a linear number of probes to a square root number of probes for success. Now, the big problem, of course, with quantum computing is the physical implementations. The universal fault-tolerant quantum computers require low error rates and long coherence times, and we're still potentially decades away from commercially available quantum computers. However, presently we have NISQ, or noisy intermediate scale devices, that are available. These are near term and are being developed by corporations such as IBM and Honeywell and made freely available through cloud backends. Now, of course, these are noisy, so they're not error free, but with enough repeated iterations of the quantum circuits, we can expect the values we measure to converge to what we should expect them to be. Currently, a popular area for applying these NISQ devices is known as quantum machine learning, and it's precisely what it sounds like. We're trying to leverage the quantum computing paradigm in order to gain an advantage for our machine learning tasks. And there's several subroutines and models that have demonstrated that this method can succeed in providing us an advantage. For the most part, currently, these are primarily utilizing variational quantum algorithm circuits, and we'll introduce more on that subject in a little bit, but for now, understand that they essentially allow for differential quantum computing and primarily exist as hybrid classical quantum models. Now, some of these that are currently well known in the community include the quantum Boltzmann machines, the quantum generative adversarial networks, graph convolutional networks, and of particular importance for this work, quantum long short-term memory models. Now, why do we care about this? Well, according to reports, quantum models can achieve just as good accuracy and performance, if not better, than their classical counterparts. But more importantly, the quantum models will typically converge far more rapidly than their classical counterparts will. Now, this is somewhat similar to the type of benefit we can see by applying stochasticity within our classical models. And given that, it's worth to point out that quantum computation itself is inherently stochastic. So this brings us to the big question of the work, that being, can we in fact achieve similar results to variational quantum machine learning by incorporating stochasticity inspired by its architectures into our classical machine learning models? So before moving forward, we need to establish the background for their case study that was performed. And as I mentioned, this is just going to start with some manner of demystification for quantum computing aimed for the novice. This is by no means extensive, so please bear with me for those of you who are well versed. So for any computer scientist and a large majority of the population, we are familiar with binary digits, bits. These are discrete zeros or ones that make up the classical von Neumann machine register values. Now, when dealing with quantum computing, instead, we have qubits. These are quantum bits, and while they are also zeros and ones, they allow for a superposition of states instead of discretely being zeros or ones. This might be a little bit confusing, but if we view the Dirac notation of the computational basis states, it might be a little bit clearer where we have zeros and ones as represented as vectors. Now, from this, we can construct a general state with a given complex amplitude for both the basis states, and this just forms any one qubit general state. But we can also tensor product together multiple of these qubits to generate multi-qubit states, as shown here. Now, given any general state, regardless of the number of qubits, we can surmise it as the sum of the complex amplitudes over the basis states. And through this, we maintain that the sum of the absolute squares of these amplitudes must equal to 1. This establishes that the absolute squares give the probability of measuring the system in the relevant basis state. Now, when we perform these measurements, the quantum state collapses to a discrete value probabilistically depending upon that amplitude. Now, as we move forward, it's worth mentioning that operators and functions applied to these qubits are implemented as matrices. Think like the matrix representation for a rotation. And within the standard representation, these will be referred to as gates, such as shown here on the right, where the wires are representing the qubits. Now, a word on these operators: they must all be unitary and reversible, where unitary just implies that the complex adjoint is equal to the inverse of the operator, giving that the operator multiplied by its adjoint and vice versa equates to the identity matrix. Now, each of these operators can be decomposed into 1 and 2 qubit gates, such as shown here, where we have our general U and decompose it into some 1 and 2 qubit gates. Now, as I mentioned previously in the introduction, this system has been mathematically proven to solve problems that have no polynomial time solution on classical computing. Relevant for this work, variational quantum algorithms, as I mentioned, essentially allow trainable and optimizable parameters to have a sort of automatic differentiation nature to our quantum circuits. Here on the figure shown, we have a data encoding layer where data X is encoded, and then this variational layer where the parameters theta is encoded. After classically reading this out, we perform some optimization on that theta before returning and running the circuit again, as many iterations as necessary. Now, this formulation has been proposed for many of the intended applications of quantum computing, and it's particularly promising since it runs on the with low qubits, such as we have with our current NISQ devices. There's various ways currently that this could be implemented and realized through software, but the one to note here that's used through this work is the Python PennyLane library. So moving forward, we'd like to now introduce the case study model that we used, starting with a brief introduction to recurrent neural networks. These are networks designed for analyzing time series data sequences for temporal dependencies, patterns, and the likes. It has a formulation for the network as shown here, where we have a cell state that loops some hidden state value upon itself a number of times before an output is read out. And there's different combinations that we could have for inputs and outputs, but regardless of the formulation, we can unroll this to have individual cells. Now, the one thing to note here is that each individual unrolled cell will be using the same network parameters. So effectively, it can be reduced to this top illustration. Now, LSTMs, long short-term memory models, are a variant of RNNs. And unlike the vanilla version, this also will loop a cell state in addition to the hidden state, such as shown, and can similarly be unrolled just like a vanilla RNN. Now, this addresses a vanishing gradient issue that RNNs have and allows the model to learn longer sequential dependencies within the data. Now, the cell construction itself can primarily be surmised as consisting of 3 gates: the forget gate, the input update gate, and the output gate. And while we're moving steadily along, I'd just like to point out that this cell construction can be mathematically expressed with these given equations here. So this brings us to the forefront of the work. We've established our background. Before we get into the analyses, I'd like to introduce the test cases you will see used throughout. The first being the trigonometric sine function. This is a widely used benchmark for implementing LSTMs and has been given regard as such throughout. You will commonly see us discussing the sine results. The next function is a sawtooth function, and this is a non-continuous function and should pose a challenge. We also tested using summed cosine waves with a waveform as shown. This is constructed from amplitudes of 1 and wavelengths of 9 and 11. The final test case used throughout is a classical physics system known as the damped harmonic oscillator. And without going into the math constructing this system, we have these equations that implement a differentiable system. And for our purposes, we use the given constants. So we've now arrived at the actual work performed, and herein the model hyperparameters shown on screen will be used. This doesn't include unique hyperparameters to the quantum models, such as the number of qubits and variational depth, but that will be mentioned as necessary. So, of course, the first step is to actually implement our classical model. While it will be sufficient to use a library-based implementation for the finer granularity and control of stochastic models, we went with an in-house implementation. This functions exactly as previously described. The only point-worthy thing to note for someone in ML is that since this is an RNN and runs temporal date dependencies, it uses backpropagation through time, which is essentially the same thing as backprop, just uses the unrolled RNNs. So with the initial implementation, we saw great success. A note on that will be important throughout. When you see best epoch being the term best epoch being used, this is referring to the epoch that produced the lowest validation RMSE value. And as we can see here, we achieved a relatively successful value with a approximately 0.17. Visually, we can see it's predicting sine well. And through our metric graphs, RMSE, MSE, and R squared, we see a nice fluid curve. This is what we expect to see. But this is fine just to say, okay, well, this is good, but we wanted to validate this. So we moved forward with a library implementation anyways, using the TensorFlow Python library. This has a construction exactly as you would expect and was very straightforward. So comparing the two, we can see that indeed we have successfully mirrored the type of success that an in-house library might show. But in fact, if we analyze the metrics, it shows that the in-house implementation is slightly outperforming the library implementation with a validation RMSE of approximately 0.17 to 0.2. This is great. It means that our model is working well. We have validated. However, in both the in-house and library cases, the model isn't performing quite as well as we would hope. We see that there's some distance between the actual sine function and what was predicted. So the solution was to use a more sophisticated optimization technique than just standard gradient descent, such as was applied here. The method chosen for this purpose was the RMS prop optimizer, and we got these results using this. In both cases, the in-house and library implementations produced validation RMSEs of approximately 0.05. This is great. We see a much more accurate prediction of these functions. So with this, we say that, okay, we've successfully implemented our model, and because of this success, we're going to move forward with RMS prop through the remainder of our tests. And so this level of success was mirrored with the other test cases. The one thing to note here, and this will be the case throughout this presentation, the model had a little bit of trouble learning the sawtooth function given its non-continuous nature. And it's reflected in its lower R squared and higher RMSE compared to the other experiments. However, rather than engineering specific settings for this, we move forward with accepting this as a valid value for success on this function. So now we have our in-house model. Classical LSTM is established. The next thing, of course, to do would be to construct our quantum LSTM so that we may compare our stochastic models to. So this is mainly constructed by replacing the multiply accumulate or MAC operations by VQCs. And this sort of translates the mathematical construction of the cell from this to this. This might seem a little bit nonsensical at first for those who understand MAC operations, since the VQC isn't inherently performing a MAC, but it is an analog and it accomplishes the same end goal, where on our MAC operations we have our weights and biases, on our VQCs we have our theta parameters. So of course, the most important thing for this construction is the VQC architecture itself. For this purpose, we adopted the VQC architecture introduced by Chen et al. In 2020 through their quantum long short-term memory paper. This has an architecture as shown in the illustration. It uses 4 wires and encodes the data x and the parameters alpha, beta, and gamma as rotation angles. And between the data and parameter encoding, we generate entanglement via rings of C-knots. Finally, this is measured in the poly-Z basis as expectation values. The one last note to make here is that there's a dashed box around this portion. That is because this is the variational gate, and it can be repeated as many times as necessary. In Chen et al.'s paper, they applied 2 variational layers, but for our work, we found that 1 was sufficient. So, how do we use this architecture? Well, as I said before, we essentially replace the MAC operations with the VQCs, and otherwise the cell construction is nearly identical. This was implemented, as I mentioned, through penny lane, using the standard qubit simulators, and had a PyTorch interface for the system. This makes it a hybrid model. Now, right out the gate, we see very good results from this implementation. Comparing it to our in-house model, we see a very similar performance, where on the in-house model we have a validation RMSE of approximately 0.05. It's slightly underperforming with a validation of approximately 0.055. Now, that's fine. We are still seeing very acceptable performance. And you notice there's slight fluctuations throughout, but that is okay. We have succeeded in our quantum model, and this level of success is continued throughout the other tests. But before we look at those, I'd like to take a look at the SINE RMSE metric plot. This gives us an idea into the convergence time. We see in the in-house model, it converges roughly around epoch 70 to its local minima, whereas in the quantum model, it's arriving at its local minimum, maybe epoch 5. So very rapid. And this is precisely what we expect to see from a quantum model, however. So we know we're on the right path. As I mentioned, the level of success for this was mirrored in the other experiments, particularly so I'd like to point out in the damped harmonic oscillator. Here we have a RMSE, validation RMSE in the thousandths, which is fantastic. We see qualitatively that it's very close to the actual damped harmonic oscillator function. This could possibly be because it's a physics-based system, but either way, it's performing very well. So with this, we have our quantum baseline to work from. So now we move towards our stochastic approaches. The first approach taken was a technique known as weight quantization. Now, this is primarily used for low precision devices that have limited computing resources and memory capacity. Through the optimization process, it will reduce the weights to quantized levels, and within, we have investigated two of the most common methods, that being deterministic rounding, where the value is rounded to the closest integer, and stochastic rounding, where it is rounded up if the decimal portion is greater than or equal to a uniformly generated random number and round down otherwise. Now, with the stochastic function, we have the added benefit that it imbues the network with stochasticity during our training phase. Now, both methods produced acceptable results. We see that there are stochastic fluctuations in the prediction on our SINE function, but to an acceptable level. And this is the case also with the metric performance throughout the training process. And the same goes for the stochastically quantized LSTM. We see fluctuations in both the prediction and the performance. However, the important thing to note here is the difference in the convergence and validation between the deterministic and stochastic versions. With the training, we see the deterministic outperforming the stochastic, but almost across the board on the validation, we see the stochastic beating out the deterministic version's performance. And this is very much so the case, in exactly what we would expect to see from a stochastic-based model. And just to make this abundantly clear, if we compare the validation RMSEs of these two methods, we see that we have approximately 0.08 to 0.05. And this is all well and good, but let's for a second take a step back and reconsider the original motivation for using this approach. So first and foremost, although it's of a lesser concern for this work, this approach was adopted to provide a fair comparison to the quantum model that has a lower number of qubits. However, it should be stated that a low number of qubits doesn't immediately imply that there is low precision measurements. So this is almost an invalid approach in of its own right. But more importantly, the main goal was to incorporate stochasticity into a classical model. And while the stochastic quantization function accomplishes this, it only introduces stochasticity during its training phase. During inference, it is entirely deterministic and doesn't use any sort of stochasticity, which isn't what we want. So moving forward, we need to find a method of incorporating stochasticity within our inference. So the approach taken for this is another somewhat common method for incorporating stochasticity into models. This is the utilization of binary stochastic neurons. And this just means that they probabilistically will assign a binary outcome based on the original activation function. And abstracting this from the MAC operation, this means that they essentially exist as probabilistic activation functions. With this, we have a manner of incorporating stochasticity into the inference phase, since they will be present during our standard feed forward. Now, LSTM models use sigmoid and tan-H activation functions, so the probabilistic result for these is given here. Now, the construction for LSTM cell using this is very straightforward. We just replace the activation functions with their probabilistic counterparts. But during backprop, the derivatives used is that of the actual activation function. And this is good. We were able to successfully implement this. However, the results, well, they speak for themselves. While it can be argued that they somewhat are learning the general trends of these functions, they it's pretty apparent that they were not successful in doing so. In fact, in the sawtooth and sum to waves experiments, we have a negative R squared value. So what does this mean for our task at hand? Well, it should be clear that this approach is a failure. It's a case of too much stochasticity and makes the model incapable of recognizing such patterns as such. But moving past that, furthermore, this also doesn't necessarily imbue stochasticity in the same fashion that we're seeing with our quantum model. So how do we rectify this? Well, for our next approach, let's first reconsider the quantum model. Within this, we have our MAC operations replaced by BQCs. Now, considering quantum computation itself, stochasticity is introduced through the measurement operations that probabilistically collapse the state based on the amplitudes. This comes in our VQCs as well as standard quantum computing at the circuit output. As such, an inspired approach should incorporate stochasticity just before the feed forward, just before the activation function in the feed forward path. So that was the immediate approach taken. So for a rather novel approach, we have applied the stochastic rounding quantization function previously introduced to the MAC operation result just before the activation function. And in doing so, we have stochasticity within our feed forward path such that it's present in inference, and this will provide somewhat of an analog to a quantum measurement operation, as much as you can state that a MAC operation is an analog, considering the placement of the function. So right away, we get very promising results with this. For the qualitative function prediction, we see stochastic fluctuations throughout, which we could expect for a stochastic approach. But when we analyze the validation RMSEs produced compared to the quantum model, we have a approximately 0.055 to approximately 0.072. This is very promising. While it's not beating out the quantum model, we have very acceptable performance, and it approaches closely to what we see with the quantum model. So with this, we can say we have a successful stochastic model. So let's now take a step back and consider the convergence on these models the success is also mirrored through the other experiments. Now, returning again to the convergence, we see here that the quantized MAC or QMAC model is converging roughly epoch 20 to 25, whereas again we have convergence at epoch about 5 for our quantum model and about epoch 70 for our in-house model. So it's a nice in-between between the standard classic and the quantum model. However, this isn't quite enough to say that we have a stochastic model that accomplishes the same prospective benefits from a quantum model. But when we look at the quantum convergence through the SINE RMSE, we see that it very rapidly converges and then spends the remaining time hunting for its global minima. However, this is a little bit different than what we see with the stochastic fluctuations in convergence for the QMAC model. So why is this? Well, let's once again take another step back and reconsider our quantum model and how stochasticity is brought into the picture for it. This is done, as I mentioned previously, through quantum measurement operations. Now, with our model, we have a poly-Z measurement, and any measurements will be computed as operator expectation values using the equation shown here. Any given operator U, we compute the expectation on the system that is in state phi. So we can also view this operator as through the spectral decomposition based on the measurement basis to give the possible measurement outcomes. Now, if we combine this decomposition with our expectation formula, we can arrive at an equation that gives the possible measurement outcomes and their probabilities. Now, through this, we have an analytical method for computing the exact expectation of a quantum circuit. And this is precisely what penny lane simulators do by default. However, for our purposes, this is not ideal. This is because such an analytical exact expectation value gives no inherent stochasticity. So as such, our quantum model isn't even stochastic at this point. Thankfully, penny lane has, real devices will run circuits for many iterations to compute an experimental expectation value. And this is what we would want to do. This is what we would like to compare. Thankfully, penny lane provides a shots parameter that lets us simulate these real measurements and expectation values. So if we set this value to 1, we'll enable low-level stochastic results that are of a similar form to what we have in our QMAC model. And right away, we can see a far more stochastic result within all of the test cases. There's stochastic fluctuations across the board, but at the same time, the quantum model is still very clearly learning these trends. Now, if we compare this to our QMAC model, we see that, in fact, the QMAC model is beating it out. For the one-shot quantum model, we have a validation RMSE of approximately 0.17 comparatively to approximately 0.07. With this, our QMAC model is outperforming a similar comparison to the quantum model. So now, once more, we will analyze the convergence using the SINE RMSE plots. The in-house QMAC and quantum models are exactly as they are, but if we look at the one-shot quantum model, we can see a very, very similar convergence to what we experienced with the QMAC model, with a convergence roughly around epoch 20 or so. And furthermore, we see the stochastic fluctuations we would expect from an inherently stochastic system. Roughly, they are quite similar. And with this, we can see that our QMAC model has managed to accomplish the same level of results that we can see with our quantum model. So, wrapping up the work and analyses, I'd like to introduce some discussion points that are resulting from this work. So, first and foremost, it should be clear that the performance of our novel QMAC model shows great promise. While the test cases run herein were really rather simple and intended to benchmark these systems and be applicable to the quantum model with low qubits, the QMAC model can likely generalize on real data sets that might be sparse and have non-discrete patterns far better than we have with our standard classical model. Another point to make, although it was not shown in this presentation, the concept of expectation values were applied to our failed BSN model and in turn produced acceptable results. Now, this bears a message to be relayed in that these binary stochastic neurons have a very similar high-level construction to probabilistic devices, and that what that tells us is that applying this manner of expectation value to these devices could produce good results. Now, a word on the quantum side of things. It should be stated that variational quantum algorithms that are targeted for deployment on real quantum hardware should first have their parameters trained by a classical simulator. Now, this might seem redundant if there is real quantum hardware available. However, if we are able to produce exact expectation values for training these parameters, we can have a far more optimized circuit than what we would see by experimentally converging our parameters. So another point to make on the quantum side is that from the work herein, we can see that machine learning might not expressly benefit from quantum versions of existing models. Now, this isn't necessarily the case if we, say, augment a network with individual quantum layers. This might produce positive feedback. The quantum models are showing success, but there's not necessarily a reason we have to completely overhaul our models with quantum layers. But they can produce good results if we use them wisely. And as a corollary for this, a wholly quantum model that's non-hybrid might produce even far better results than what we could expect. Now, of course, it would be remiss to not leave off from here without a statement that this was done as a case study and that there might be potential differences in findings when analyzing other models. And this is a manner of future work, so to speak. So in conclusion, I'd like to bring us back to our initial question. Can we achieve similar results to variational quantum machine learning by incorporating stochasticity inspired by its architectures into classical machine learning models? Well, after going through all of the work and analyses, I like to think that it should be apparent that yes, we can, and it is possible to realize similar performance. This concludes the presentation and what I have to show for you all. I thank you for your attention.